All right, I think it's going. Okay, so we want to talk today a little bit about friction problems and try to get some of the trickier ones. And I want to start with 6.19. This is exactly the same as the other class if you already watched that live stream, although we may deviate depending on what questions come up. So at least we're going to start the same way. I'll give you a screen share to get this rolling here. Oh, we don't want this. Let me see. I don't want this one. I want this one here. Okay, there's the solutions. And then I think I want to start up here. Yeah, there we go. So we are looking at 6.19, all right? So in this case, we've got a zombie is going to push on some blocks. Starting from rest, the bottom block is pushed horizontally with force magnitude F, and it accelerates to the right. Okay, and so the frictional coefficients between all surfaces are some numbers here, and the two blocks are observed to move. All right, so let's kind of get a feeling for this here. This was working for me earlier today, so I'm going to do it again. The idea here is we have a calculator, and we have this, what is this? Some paperclip holder, okay? So the idea is I could push this thing, and the idea is if I push this thing around, if I can get out of the way, you could see that the calculator, I'm going to push horizontally on the calculator, and this thing is going to come along for the ride, all right? And so that's the basic physics here. It's nothing too crazy. We push on the lower block, and the upper block comes along for the ride. Okay, so let's go take a look at that again. And, oh, this was important. The two blocks are observed to move together as a single unit. M1 does not slide relative to M2. That means we're going to be able to do a system FBD, a block 2 FBD, and a block 1 FBD. So right now, I'd like you to take a minute to try that. I'll leave this up on the screen, and I'm just going to scoot this a little bit lower so I'm not distracted. There we go. So try to draw the FBDs, and then I'm going to ask you to help me walk through it in just a minute. So give yourself a minute to just think whatever you want. Try not to look at the solutions at first, okay? If you finish and find yourself waiting for me, then go ahead and look at the solutions. But try to write the FBDs and force equations without the solutions, because they're not going to help you on test day. I'll give you one more minute. All right. Oh, and I should probably have this page open so I know what I'm doing when I stop the screen share. Got it. Okay. All right, so try and help me through this now. We got block 1. Somebody tell me a force acting on block 1. Anything.
Gravity.
Okay, what should I label that?
M1G.
Nice. Okay, another force.
Friction.
Okay, okay, which way is friction on block 1?
Since it's moving relative, so I'll go to the right, right?
Absolutely.
Because it's not, I don't know how to explain it.
Okay, let's take a look. Okay, was that Kevin?
Yes.
Okay, Kev. So the idea here is, and by the way, I have no idea which way it looks like right on your screen, and I don't really care. So we'll just use the words forwards and backwards. So for right now, let's call this way forwards, okay? So when I push this thing forwards, what is the force that makes this thing go forwards?
Friction.
Yeah, what would happen to it if there was no friction?
It will just slide off.
Yeah, so its tendency is to slide off the back. That means friction is in the forwards direction. So going back to our picture here, give me a sec. Going back to this picture, we know that if you're pushing this thing forwards, the tendency would be for one to fall off the back, which means friction has to be forwards on it. Otherwise, it would fall off the back. Nice job. Okay. So there's friction here. Anything else on block 1?
Normal force 1, 2 going up.
Exactly. So we're going to label it 1, 2 because it's between blocks 1 and 2, not from the floor. And then I think that's it. And I'm just going to, they all move together. So I'm just going to do one acceleration up here. They're all moving this way with acceleration A. Got it. Okay. Anybody? Something on block 2?
Yeah, force, capital F.
Okay. The zombie, applied force, whatever, F. Got it. What else?
Friction going
to
left.
the left.
Okay. Which friction? From the ground or from block 1 or what?
From the ground.
Okay. So I'll give that, since it's from the ground, I won't use any subscripts for it. And obviously, I could do friction subscript 2, but I don't really need that. What else? I'll do the obvious. I know there's that. What else we got?
Would it be a
Normal
normal
force.
force?
Normal force from what?
1, 2 going down.
Ah, good. Right? If 2 pushes up on 1, then 1 pushes down on 2 with a normal force. Okay, what else we got?
You've also
There's
got
also
a normal force
from the ground.
Yeah. And then that one, since it doesn't really matter, I'm just going to give it no subscripts. So the 1, 2 will be the one that's between them, and the one without this would be the one that's from the floor on the bottom block. Again, sometimes you might choose to just say this because it's on 2 from the ground. That would be another good way to do it. For now, I'm just going to leave it like that. All right. So are we done? Are we ready to move on to the next one?
So shouldn't you still have friction 1, 2 on that FBD?
Oh, if so, which way?
To the left?
Exactly. What's your reasoning?
Well, it's a action-reaction pair, so it has to.
Absolutely. And now, while what I'm about to say is not precise English, I think it makes the most sense. 2 frictions to the right on 1. Therefore, 1 frictions to the left on 2. The sentence makes sense, except frictions is not a verb, but you get the idea. You know what I'm saying? So 1 exerts friction to the right on 2. Or wait, what did I just screwed it up. Object 2 exerts friction to the right on 1. This is on the 1 FBD. So 2 exerts friction to the right on 1. Therefore, 1 exerts friction to the left on 2. All right. Now I think we've got it all, right? I think so. All right. What's the system?
Capital F going right.
Mm-hmm. What's the weight force going to be now?
M1 plus M2 G.
What else?
Normal force going up.
That's still the same. Don't need a new label. And this is still the same. What else?
That's it.
That's it. Notice which forces here are the internal forces.
Friction between the boxes and the normal force between the boxes.
Absolutely, these two, the blue ones, if you could see it. So think about it. The System FBD is basically a pictorial addition, right? This arrow and this arrow combine to make that arrow. This arrow is still there. The two green arrows are right there. And because these two point that way versus this way, these two blue arrows cancel out those two blue arrows, and they don't appear in the System FBD. So far, so good? All right. Let's go take a look at the next question. That was outstanding work. Oh, wait. Don't we need force equations?
Yes.
Okay.
No,
take a second to write them really quick. Did you guys already get them? If you haven't already written the force equations, take a second to do that. I'm going to run out of room here, so I'll do a quick screen share in just a sec. So I'll give you 1 minute just to make sure you can do it. Again, try not to look at the solutions. I'll give you 30 more seconds, then I'll show it up on the screen. All right, here we go. Sorry if I didn't give you enough time, my bad. Oops. My gosh, it's somewhere in here. There we go. Okay. So hopefully you're feeling pretty good on that. Fortunately, I even remembered to double check the color coding before class today, so I got the same colors. All right, so hopefully that's good. Any questions on that? That's 2/3 of the problem, pretty much. Okay. Whoops. Oh, we need to see the question again. Let's see the next part. I think that was part A, right? Okay, we did all of part A, all that crap. So now take a look. We're supposed to figure out F12 and F. So we're given the masses, accelerations. So M's, A, and G. Got it. So in this case, these are our givens. If those are our givens, which force equation looks like the best to figure out the things that we want? And remember, what to find was we're looking for capital F and the friction between the blocks. What do you think? Which set of equations would you use?
Block 1x looks good for the friction.
We know the mass. We know the acceleration. We are done, right? Okay, what about F? Capital F. Which set of equations looks like the best to get capital F?
I would probably go with. Well, we would have to first figure out friction, then probably use system FBD.
If we could just figure out that friction, you're right. There we go. Now here we know this, and we still don't know that. So either one would work. Do you agree?
Yeah.
However, this one's a little bit simpler, but we see that we do need to figure out that. Well, how do you figure that out? Let me do this. Okay, so I'm going to ask you a couple of questions here. So in this case, sorry, there's a little glare there. It's a little better. Which of these equations applies? Does F equal mu static times the normal force, or does it equal mu kinetic times the normal force?
Mu kinetic normal force because
Okay.
it accelerates.
Exactly. It's moving relative to the floor. Okay. Now, in this case, do you agree that we could figure out the normal force is equal to this? The ups equal to downs because there's no acceleration in the y direction. Again, there's no acceleration up and down. That means the up and down forces have to balance. Does F equal little f? Does capital F equal little f?
No.
No. In fact, which one should be bigger?
Capital F,
Yeah, how can you tell?
because it's going right.
It's not going right. It's accelerating right. There's a difference, right?
Yeah, sorry.
Going to the right, you could be going to the right at constant speed. If you go to the right at constant speed, what would the acceleration be?
0.
And in that case, what would be true about these?
And they're equal.
Yeah, so we have to be a little bit careful. If you accelerate, so look for the words. I'm just trying to be picky there, just to, try and help you be better. That's all. All right. So at this point, I think we could go back and solve that. Let me just go back and look at this. So in this case, we know the normal force. We know we can get the frictional force from that using, just give me a sec, F equals mu kinetic times the normal force, which is this, which then that plugs in right there, and then you could solve for F, and we got it. So far, so good? I got to sneeze. Man, that was a big one. All right. I have one more question for you here. So obviously you could do the math. What's more important here is that I teach you the setups and the tricks about the setups, and you go through the algebra at home because you've got the book and you know the answers and you could do it. Obviously, I'll answer your questions if you have them on the algebra, but most of you, it's about which way do the arrows point? Because after that, it's pretty straightforward. So let me ask you this. So if we wanted to figure out friction 1, 2, we could relate that to the normal force 1, 2 in theory. So which of these equations applies for friction 1, 2?
Well, it would be less than static because we don't know that it's on the
Nice.
verge.
Exactly. This is not true, and this is not true. Just because it's moving doesn't mean kinetic friction applies. Look at this case. Nice job, Esteban. I was trying to trick you, and I can't. So the idea here is if I move this thing back and forth, it's not on the verge of slipping. So it's not moving relative to this. It's not moving relative to this means not kinetic friction. It's not on the verge of moving relative to that. Now, if I go really fast, there it was actually slipping, right? If I push really hard, it does slip off the back, and then it's kinetic friction. And then you could figure out, well, yeah, in this case, it's just no indication is made that it's about to slip like that. So we would just say, well, in fact, we already told you friction is mass 1 times A. We don't even need these equations, right? So, all right, good job. Let's take a look at the next part. So at this point, I guarantee you could plug in the numbers and get part B based off what you've told me. So now let's say we did the same masses, and I want you to determine the maximum possible F for which the blocks move as a single unit. Would the free body diagrams change? Yes or no?
No.
Okay. Would anything change? We were just told the FBDs wouldn't change. So the force equations wouldn't change. Something's got to change. Otherwise, it's not a different part. What changes?
What was the question again? I'm sorry, I didn't.
We're trying to figure out the maximum possible force you could apply for the blocks to still move as a single unit.
So I mean, it has to be less than U static. It can't be greater than U static because then they wouldn't move in the same place.
So what you're saying is part C says max possible F. That implies U's friction 1, 2 does equal mu static times normal force 1, 2. Whoops.
Yeah.
That's true, but what else will change? Something else must change as well.
Would it be the acceleration?
Absolutely. This is not going to be the same number anymore. It's still going to accelerate. It's still going to accelerate to the right, but it should be a bigger number than what we just had, right? Otherwise, that would have slipped. So the idea here is these are the two ways you could imagine phrasing this question. This block could be on the verge of slipping, and this rule applies, or it could be not on the verge of slipping, and then we just use F equals MA. All right. Nice job, people. What do you think? Is that good?
Yeah, I think so.
Should we try another one? Let me see here. Let's try, let's mix it up a little. Let's try 6.24. I'll screen share, okay? 6.24, just so I'm not doing the same damn problems all day. They're all good. I'll give you 2 minutes to look at it and start it. So again, look at it, start it. If you have a question, you can talk to Memo, send him a chat, whatever you want. I'm going to get this erased and get ready to rock here. And then what time is it? So this is at about the 30-minute mark. Okay, just make it a note. 25-minute mark. That way I'll tell the other class if they want to see some different problems, they can know it. And so that means probably at about the 30-minute mark. I'll send an email later. That way you guys each have it. Okay. All right, whatever. Okay. So some of these problems, you'll see where it says the coefficient of friction between the two blocks is mu. So this is basically me getting really lazy and basically assuming mu static equals mu kinetic is both equal to mu. So that's just me being lazy, okay? It's bad form, but yeah. Sloppy. So we're going to assume both of the frictional coefficients are the value mu. That way I don't have to deal with the subscript on that. All right. Let me get my, okay, got it. All right, so let's do it. So give me some stuff on, I'll do this one. I know there's an M1G, or we'll just call that MG. And this one should be 4MG. What else we got on this? Either one. Tell me an FBD, tell me a force, tell me what's up.
We got normal force on 4M.
Okay, going which way?
Going up.
Up, okay. All right, what else?
We got a thrust force to the right on 4M.
Okay. Is there friction on the ground on this one or not? I don't think there was, right?
Friction
No.
on the surface.
Okay, negligible friction with the ground. Okay. Anything else on this one?
There's N12
Oh, which way is that?
to the left
How do you know that?
because it's pushing on M, so M is pushing back.
So on M, there's a normal force this way. So then on 4M, there's a normal force back. Action, reaction. All right. Getting a little glare there. It's a little better. Okay. Is that it?
Is there friction on the two blocks?
Ah, yeah. Between the two blocks, there is friction. Which way?
Is it going right on 4M?
Nope. Let's take a look at it. It's a good guess.
So it should be up on M
Yeah.
and
Think
down
about
on 4M.
We know that there needs to be friction on this one holding it up. So by Newton's third law, it appears that way on 4M. Got it? Does that make sense? So the normal force and the friction, right? We know there's a normal force 1, 2. And notice they always form these right angles, the normal force and the frictional force. Do you agree? Friction is a contact force parallel to the surface. Normal force is perpendicular to it. Exactly. If there was no friction holding it up, it would fall down. So that's what tells us there must be friction holding this one up, which means there must be friction going down. And so we would actually say these two blocks are coupled by friction. It's a little bit like it, Esteban. A little bit. We'll get to that when we get to Physics 161. Okay. There's a carnival ride, yeah, that relates to this. And that's, well, if you care. Usually I do that as problem 6.57, if you want to know. But yeah, we'll worry about that later. All right, then these things are accelerating to the right, aren't they? Is it legal to do a system FBD?
Yeah.
Yeah, so let's do it. So which forces are not going to appear?
N12 and F12 are going to
Yep.
cancel.
So then we know we have this. No, we have this. And then down, what do we have?
That'll be 4m plus m times g, or just 5mg.
Nice. All right. From here, you could write some force equations, solve for some crap, right? And it says, what is the minimum? Okay, let's read the question again. Okay, so again, do FBDs. We should write the force equations, but then it says, determine the minimum thrust magnitude required to prevent this from sliding downward. When you see all those words, what do you think? I want you to think something when you read that.
Well, we want to know what the maximum friction is before it starts going. So, well, no, we don't want to know the maximum friction.
Right. I get your idea. You're thinking, what's the equation about friction I can write down? That's what I'm asking.
Right.
What is it?
It would be mu, because they're both the same. It would be mu normal force.
Yep. And so in this case, we would just change that out to mu. And so this applies. Awesome. Okay. Does that make sense? So in this case, we actually have how many equations here? Let's take a look at the board here. So this would have two force equations. This has two force equations. And this one has two force equations. And then we just mentioned that, aha, on the verge of slipping, and what were the words? It was max possible thrust. Those were the key words. Or was it minimum possible or something? I think it was min or whatever. Something about that. It was either a max or a min, one of those words in there. And so that told us there. Now this is going to be a little subtle here. How many equations, how many useful equations do we have then to work with this?
Two.
In all of this problem, how many useful equations do we have?
Oh, 4.
5. This is subtle. These two equations produce those. So these two are redundant. They're not unique. Or you could use this block and this block to reproduce that one. Or you could use these. So basically, even though it looks like we have 6 down here, there's really only 4 useful ones. And these two look like the most useful. They're the easiest. So remember, these two pictures produce equations that would produce this picture. So this is redundant. So and then the friction equation is the 5th hidden equation. So we actually have 5 equations here. All right. That's what I was trying to go for. Did that make sense, Jake?
Yeah, it is subtle though.
Yeah, another way of saying it, if you know anything about math, we'd say these two equations are linearly dependent on these 4 equations. We often talk about writing systems of linearly independent equations. That just means basically these 2 equations can't be created from those 2 alone. These 2 equations can't be created from those 2 alone. However, these 2 equations can be created from all 4 of these. And that's the subtle difference. Because these 2 can be created from them, we say they depend on them linearly, right? They're linear equations that you could create from the other ones. All right. Anyways. All right. You could do this more at home. Let's practice doing as many setups as we can. All right. So after this, you'd write some force equations, plug in some crap, do some algebra. I'm going to let you do that at home. Let's go to another problem. Here's a favorite of mine. Let's try 6.21. I'm going to give you a couple of minutes. We'll say till 2:55 there or something. I'll get this out of here. There we go. Okay. Let's go ahead and take a look. Okay. So in this case, just to give you a visual on this, to make sure you believe this is not impossible. So we've got our calculator sitting on our book. That's going to be like the sled. Now, when I put it with the rubber feet down, it's got a very high coefficient of friction. If I flip this over, I hope you agree it's got almost no friction to hold it in place. It's pretty easy to move. Now, to make this really cool, I found some old CDRs. Oh, yeah. And that's going to be the thing, the big heavy object I put on top of here. Okay. And in case you don't believe me that this is really possible, clearly I'm going to attach this to the upper object, and I can make this thing move around if I can actually get it centered on here. Whatever. The point is, if I pull on this, I hope you agree, I'm pulling on the upper object, the CDRs, and the, gosh, you can't see it at all. I got to hold it out here like this. Right? You could actually see the calculator move. Oh, now it slides relative. It's pretty difficult to do this. There we go. So I could actually pull on the upper block and make the lower thing move if, like I said, you have to have basically negligible friction down here at this interface. By putting the buttons on there, these hard plastic buttons have negligible friction. Okay. It works. So now somebody give me one force acting on the sled.
Gravity, mg.
And that's just mass m. Man, it is so hot in this room right now. I am literally dripping sweat. Okay, what else we got? I got the two gravitational forces.
So on the sled, we've got normal force going up.
Okay, from the ground?
From the ground.
So I'll call that just N without any subscripts. Okay, got it.
And
What
then
else?
Also on this slide, we have a normal force from the box going down.
Wait, shouldn't that just be 2 mg?
Yes.
We'll find out. That's not the case. So you did it correctly, Jake. You said, I know there's a normal force down on it. A lot of times students like to say, well, shit, man, this other box is sitting on there. Isn't it just the whole weight of the other box? No, not always. You can't just assume this normal force is equivalent to the weight. We'll see in just a minute. All right, what else you got? So, Jake, good job. Is there friction on the... There was negligible friction from the ground, right? So this was 0, I think, right? There was negligible. Is that right?
Yeah. Yes.
So I can get rid of that.
There's friction to the right, though, between the box and the sleigh.
Okay, so on this one, you said it's to the right?
Mm-hmm. That's what's pushing the sleigh that way.
Okay, and so absolutely. Because we're pulling on this one gets dragged along with it, right? If there was no friction to the right, the box would just go off the top of the sled. So there has to be friction there. Okay, good. So immediately, somebody other than Esteban, what does this tell us about this block?
We've got friction going to the left and up, or a normal force up on box 2.
Beautiful. Action reaction pairs. Anything else? I think we're told it accelerates, right?
Yeah, to the right.
Okay.
And then box 2 has a tension force going upwards.
Okay, like this
on
one.
the right. Yeah. And I believe that's it on the box.
Okay. Is it legal to do a system FBD in this case?
Yeah, the
Yep.
normal force and frictions will block out.
Yep. So then that's going to look like what would be down?
Three mg.
Yeah. So if I made these arrows a little better. Yeah. So hopefully they look a little bit more realistic. That doesn't matter that much, but you get the idea. 3 mg down. What's to the left on the system?
Nothing?
Exactly. Sometimes people feel uncomfortable. Now, this is legal because it's accelerating to the right. It's okay to have an unbalanced force to the right. Now, check this out. I want to point this out. Take a look at this one. Let's do the Y force equation for this problem here. Do the Y force equation here. What do we get for the Y force equation? I think this was theta, right? We'll call it theta. Who cares? Give me the force equation in the Y for block 2M.
So you have N12 plus tension sine theta minus 2 mg.
Equals mass times acceleration. What's the acceleration of the Y? 0. Is that what you said, Esteban?
Yep.
Looks good. Check the chat here. Nice, Jesus. Sorry, it took me that long to catch up. Sorry, dude. All right. Okay, so in this case, I just want to point out, I was trying to trick Jacob earlier into thinking N12 was 2 mg. But do you agree from this equation that N12 is not 2 mg? It will be 2 mg minus T sine theta.
Yeah, that makes sense.
And so this is what I've discovered students sometimes get in a hurry. Jake did it perfectly when he said, just write a normal force. Sometimes students will cheat and say, well, shouldn't this just be 2 mg? Evidently not. Anytime you have a tension at an angle, it could get sketchy. In a lot of the problems we've done up to now, the string was parallel to the plane or whatever. We didn't have a weird angled string. If you have something like this where it's angled, think about it. These two forces support the weight. So the idea is if the zombie's lifting up on the box a little bit, number one only has to support some of this 2 mg. And by Newton's third law, only some of 2 mg pushes back down on the sled. So far, so good? All right. So in this case, we could write down force equations. I know you can do that, or you can read the book. Now, in this case, what I want to know is we've got a friction. So Jacob and Esteban have been answering a lot today. So let's let somebody else have a shot at this one. Which of these equations do you think applies here? Is it going to be mu static or mu kinetic?
Wouldn't it be mu kinetic since it's the hold-on rate?
Okay, it's moving, right? So the logical thought is if it's moving, you got to use mu kinetic. However, that's not right. Let me show you. Hold on. Oops. It's not moving relative to each other. That's the friction in between here, right? And so in between there, I don't know if you can see that little gap there every once in a while, but it's not moving in between there. So the CDs are not moving relative to the calculator. Down here between the calculator and the book, you could use mu kinetic, but we were already told that's negligible. Was that Kevin?
Yes.
That makes sense why we don't want to use mu kinetic?
Yeah, because the only thing that's moving is the calculator. That's
Exactly. The calculator is moving relative to the floor. So so we don't use mu kinetic. All right. So then what should we use? Let me rephrase. So can we just use this one then?
Yeah.
No, we can't use that either. Trick question. It's not on the verge of slipping. Don't you love it? I was deliberately trying to mess with you and I did. So I'm trying to mess with you now so that on test day you can get it right. That's my goal here, not trying to be a dick. All right. That's just a nice side benefit for me. Let me go into here. I really am trying to help you with this. Take a look. It says the box does not slide relative to the sled, but it doesn't say it's about to slip. Do you see that? And look at part D. Compare this to it's not at its maximum possible value. So in this particular question, I even gave a hint there that, okay, the maximum possible value is mu static times the normal force. So what if I'm suggesting you compare them, that means they aren't the same, which means it's less than. So I've deliberately been trying to trick you all day because this is a very confusing thing. The idea is there's one more case that I haven't been writing. Remember, friction could be less than, and this is the one that applies. So sorry if I messed with you there. But is that making some sense?
yes.
Okay.
Makes perfect sense.
It's tricky. And so there's only one way to do well on this section. Lots and lots of practice. Unless Memo, can you unmute and tell us the secret sauce to succeed? What do you recommend to these students? If you got your camera and want to turn it on, I'll put you on screen. Oops.
The success to these problems is doing as many problems as you can, and yeah, just drawing your pictures. I was going along the whole time.
Yep.
Just doing these problems.
Yeah. There's no real secret sauce, I don't think. It's just practice, practice, practice. How much did you practice for these before you got good at it? How many did you have to do? About 10 or 20 or?
I'd say about like, yeah, probably like 30 maybe. I would do problems in the book and practice on the practice test on Georgetown's website.
Yep.
And just thinking about it critically too, because you will come across stuff like, is this mu static? Is this mu kinetic? Or what is this? Just like, yeah, just figuring those parts out is the most difficult. But once you get that down, once you get the concept down of what type of friction force to use, then you should be good to go. Just understand the concept first, and then get that in the problems.
Yep. And so, and you'll get it. All the problems, it's like I keep trying to lull you into, oh, I don't have to think too much, and then I'll sneak one in where you have to think all of a sudden, right? So you'll do 2 or 3 in a row, which don't seem that tricky. But each one of these problems, let's go look at them. Thanks, Memo.
Yeah, no problem.
I'll give you a thumbs up, Memo. There you go. All right, so let's go back to here.
Yeah, that was a good trick, using the mu static, like, oh, which one is it, mu static or mu kinetic? And it was neither.
Yeah, exactly. So that's what you do to students, to be mean to them. But you try to, and then you try and phrase your voice like, oh, it's got to be one of these two, and then see if you could trick them into it.
Yeah,
so,
they won't forget. They won't forget that.
Yeah, exactly. So here's one. Something weird about this problem is, oh, this is comparing what happens if you pull up the plane versus down the plane. So that's what's good about this one. Okay. And then let's go take a look at this one. This one is a little bit interesting. 2 blocks are connected by a string. They're released from rest. Between the larger block and the incline, there's friction. Everything else has no friction. So here's one. Could you treat this as a system? What do you think, class? Anybody? 6.22. Can we treat this as a system?
Probably not.
You could, but it's not advisable. Technically, they're going to move together, right?
Yes.
But the hard part is there's no friction here. There is friction here. And so if you don't draw them separately, you might not have the right normal force to figure out the friction. So that's what this one's all about, right? Let's keep going. How about this one? It's lowered at an increasing rate. What does that tell you?
Acceleration down the plane.
Okay, what if it was lowered at a decreasing rate?
Negative acceleration down the plane.
Which would be acceleration up the plane, right?
Yes.
So these are the kinds of ways I mess with students on a test. What I could do is I could basically give you the same pictures, but make one of them raised at a decreasing, or raised at a increasing, or lowered, you know, etc. Basically, this changes the direction of the acceleration and the friction. Because it's lowered, which way does friction point?
Up the plane.
Yeah. Is that going to matter if it's accelerating down or up? So let's look at part B. In particular, in part B, what's that going to do to the friction direction? If you're lowering it at a decreasing rate, you accelerate up the hill. What happens to the direction of friction?
It flips.
Nothing. I was trying to decoy you, right? The idea is you're moving down the plane. So friction opposes motion, not acceleration. If you're moving down the plane, V would be down, A would be up. Friction opposes the velocity, right? So that's what this one was all about. Now we did that. Let's keep going. This one, the idea with this problem was it was to show you that sometimes normal forces can be left-right, and sometimes frictional forces can be up-down. All right, so that's cool. Make sure you do this one. Part B is kind of fun. All right. This is a great concept question. I'm going to let you do this one on your own. Let's keep going though. These are the ones that you're not required to do. We'll do those in the next semester. But if you want to, you can, but they're pretty tricky. Here's one. This is, okay, you got a block pushed with a force magnitude F along a ceiling. This can actually happen. We're going to assume all the coefficients are there. Okay, so we've got mu there. All right. Let's do the FBD on this thing. Somebody tell me a force. I got one. Here's F. Give me another force.
mg down.
What else? I see in the chat. Let's get the chat there. Normal force down and left. Excellent. Perpendicular. So this was the point of this one. Normal force can point down. Anything else, or are we done?
There's another normal force into the ceiling, right?
That's on the ceiling. Does that appear on the block?
Oh.
You're
No.
right. There is another normal force, but that acts on the ceiling. That doesn't appear on our FBD. So anything else?
Do we have friction up the plane?
Let me see here. Friction left along the plane. I think you're right. Whoops. Oh, I'm on eraser mode. Come on, there we go. And remember, notice friction and normal force, even though the normal force can point in weird ways, use that trick. We know the normal force is perpendicular, and then you know friction's either this way or that way. Now, in this case, because it's moving kind of down, since it's moving this way, that's the velocity. That means the friction is opposing that. Nice. Cool. Let's keep going. Oh, to get a feel how crazy this is, it's not impossible. It's just really, really challenging to create. Let me show you the picture of what this looks like. I think you'll laugh. I have a strange idea about what makes people laugh, I guess. Where is it? 628. Oh my gosh, come on. Look at us. Look how much force you would have to apply compared to the weight, right? So this is actually to scale. If you are thinking it is implausible, you are correct, but it's not impossible. It's physically possible for a very short time interval. So let's say you have an eraser that weighs like 1 pound or something. You'd have to push on it with like, oh gosh, like 7 pounds or something. Okay. Yeah. Sure. True enough, Jake. True enough. I have strange, I don't know. I find this stuff. Look how fast this thing would accelerate too. It's like, it's a very crazy looking problem. It does work. Oh, so it looks like it was about 5 times the mass there. So that's pretty crazy. And the acceleration, look at the acceleration. That's more than free fall. That's insane. You would have to push this thing really hard and really fast. And in practice, you wouldn't be able to keep it up, right? You might do it
like it would be like a firework hitting a ceiling.
Yeah, you could put a firework in there and launch it against the eraser and have it go for a few seconds. Now, with your hand, you could clearly move your hand faster than free fall, right? So like the idea is you could you can get your hand below a marker for about this much distance, but not much more than that. So you could do this for, yeah, anyways, enough on that. All right, let's get back. Rapid fire. Are you guys digging the rapid fire? Just try to look at as many problems and show you the physical reasoning. Is this working or not?
Yeah, so I was gonna say that problem was similar to one of the questions from the quiz.
You recognize it, don't you?
Yeah.
Yeah. The only difference was the one we did on the quiz had no friction, right? Yeah. So good job. Nice. Let's go back into here. This talks about, at some point, you probably remember me mentioning this one. Look at this one. If you're pulling up and to the right at some angle, at some point, the block lifts off the ground. And so this helps you understand that. Now, notice there's a part here that requires calculus. That's actually the interesting part of 6.31. It turns out there's a certain angle that helps you accelerate the most. It's not straight to the right. It's not straight up. We see that it's at some angle. And so that's what's really cool about this problem is it shows you why it's easier to pull things slightly upwards at an angle. I think this would make it clear. Watch this. I find this interesting, so I'm going to show you on the whiteboard here. This is just kind of a little like a conceptual feeling for trig. If you look at this, let me try and draw a vector exactly to scale. Let me get something I can draw to scale here. Okay. So the idea is I'm going to draw this horizontal vector like this as long as the book. Okay. And now I'm going to do the same one at a slight angle. And I want to point out, technically, it's not quite as big, right? They both go, so there's a small change right here. However, the horizontal component is almost as big. Okay. However, we do get a vertical component now. And the idea is this. If you pull at this weird little angle, you pretty much have almost the same horizontal component, but because you're lifting up on it, you need less normal force. If there's less normal force, there's a little less friction. Now, at some point, if you go too high at the angle, there's a trade-off. You get a lot less friction, but you also get a lot less force this way. And so these three black solid line arrows, whoops, not this. They're all the same size. And the idea is at some point, you know, if you pull straight up, it's not going to go anywhere. But you see that at some point, if you give it a small angle, you're going to basically go, you'll have the same force to the right, but a little bit less friction. That means more acceleration. All right, whatever. Maybe this would be a good idea to be if you're a suitcase designer and you wanted to figure out the optimum angle to pull something, although you could put wheels on a suitcase and that would help. Then you don't have the friction problem. All right. Anyways, that's what's interesting about that one.
What determines that angle?
The coefficient of friction. It turns out it's something like the angle to pull at tangent theta equals mu static or something. So you could look it up in here. You want to just look at it really quick for fun?
Sure.
It's the next problem in the book. So it turns out the optimum angle is this. And so I kind of walk you through that. That's how you would get there. It's this big, ugly equation here gives the acceleration, right? You take the derivative of that with respect to theta, set it equal to 0, solve for theta, and you get this. Oh, excuse me, tan inverse of mu kinetic. Sorry about that. So, all right, that said, let's keep going. That's kind of fun, right? It relates to the frictional coefficients. This is a similar problem. And actually what's cool about this one is you realize pulling up and to the right and pushing, it's similar. And so you get to see what's different about pulling up and to the right versus pushing. Now, when you push down, this is a problem because when you push down and there's mg, you need more normal force. You've got to account for the mg and the p cosine theta or whatever, p sine theta. All right. Here's one. Let's look at this one. 6.33. In this case, okay, so M2 is much bigger than M1. There's no friction here, no friction there. Now look at these coefficients of friction. Do those look big or small to you?
Small.
Looks small.
Small. This is like ice or Teflon. So very low coefficient, less than the calculator probably. It's small, but we're going to assume it's not zero. You'll see why in just a minute. So now, do you agree theta is big? Which direction do we think block 2 is going to move? Is block 2 going to move up the plane or down the plane?
Down.
Down. Do you think it's going to accelerate or not?
Accelerate.
Yeah. Okay. So this one's going to accelerate down the plane. So what is 1 going to do? They're connected by an inextensible string. What's 1 going to do?
It's going to accelerate in the opposite direction.
Okay.
Same.
Is that, yeah, the A is the same here, right? A equals A. So in this case, what are the internal forces? What are the forces between these two?
Tension.
Okay, there's a tension force right here. Excellent. What else? There is
Normal
friction
force?
here. There's a normal force up on this one and down on that one, right? Anything else? There is something else. What's another force between them?
The weight force.
Nope.
Friction.
Friction. Which way does friction act on 1? On 1. Up the plane or down the plane? Which way is 1 moving?
Oh, down the plane. So M1's moving up the plane.
1 moves up the plane, so friction is this way. So then which way is friction on 2?
Up the plane.
Yeah, think about it. 1 is trying to drag block 2 up the plane, while 2 is trying to drag block 1 down the plane. Now, in this case, do you agree they have the same value for A?
Yes.
So what do you think? If we did a system, which forces would drop out?
Tension. No. Friction and normal force for sure.
I just
But I'm
set
not
you
sure
up.
about tension.
Sorry, Jake, I did it to you again. You can't draw a system
okay.
for this. You can't do a system. They have the same A, but are they moving together as a single block? Are they accelerating the same way? No.
Oh, nice. No,
So
they're
you
not.
can, yeah, I tried to, this is the one that shows you just because you have forces that are internal doesn't mean they drop out. In this case, this one's accelerating this way, this one's accelerating that way. They do not move as a single unit. A second later, right, it's going to look like this, where the blocks are not in the same positions. It turns out when you do this problem, this is a very sneaky problem. I discovered this. This was one of the first problems I put on a test that just failed the whole class. It was, so I'm like, man, why did they not see this? I think a lot of people thought you could use a system on this is what I learned. That's what I put it in the book for. Let's go take a look at this one. So this is number 33, I think. Okay, so this is what I learned when I wrote up the solutions for that. I'm like, people, just because they have the same A doesn't mean they move together as a single unit. So don't do a system FBD. It's friction. Now look at this. This is crazy. I hope you agree with those. I'll give you a second to look at it. If it helps, maybe I could do this. There it is. So you could see them at the same time. Sorry, it's kind of not perfect there. So here's block 1. Here's block 1. Here's block 2. So that's this one. And look at this crazy thing that happens. The friction is negative on both of them, and it doesn't cancel out. If you recall, you could run your coordinate system going this way, and then you change your coordinate system as you go around. If you're really going to treat it as a system, you have to do that trick, right? And so when we see this one, if you want to do that, you're right that the tension would drop out, right? Because notice the tension is negative on this one, positive on this one. The normal force would, let's see, normal force would be, actually, that's kind of weird. I don't think the normal force drops out either. Do you see that? It's positive here and positive there. And so here, look, this one is negative. This one's also negative. So the friction doesn't drop out. We see that it actually doubles. Isn't that cool? Or torturous, one of the two. So that was the point of this one, is to realize 2 separate FBDs always works. Doing a system FBD sometimes can be tricky. That was the point of this one. All right. I don't know if I'm killing you yet. I'm going to keep going. What the hell?
So you,
oh, go ahead. Yeah.
so you could use a system, but it would just make it so much worse on you. So.
You would use it.
Is
You
that
could
right?
try to use a system, but it's very confusing. I wouldn't see that the frictional force contributes double. I would have thought the frictional force drops out, but it doesn't. So the moral of the story is, if you have a system FBD, you could always draw separate FBDs as well to double check the system. You know what I'm saying?
Okay. Yeah.
So just because you don't have to do that extra FBD, I still would do it anyways. Oh, yeah. Oh my gosh. These are starting to get a little crazy here, but yeah, you could do these things. All right, there it is. So it's 3:33. You know I love triple numbers. That's it for this course, people. On Wednesday, I'll just be here and we'll do extra problems. If you don't want to show up on Wednesday, you don't have to show up. If you want to show up Wednesday, go for it. I'll be here and I'll just answer your questions. So try to get chapter 6 done. And if nothing else, try to find things you don't understand in the solution so I could try to help you. Because I want to actually help you with things that are confusing. All right.
This next test is on Monday, right?
So let's take a look at the course overall where we're at. So, whoops, that's for you. I'll show you that in a minute. The first page. This is, oh my gosh. Just give me a second.
And then also, when are we going to be scheduling for the oral exam?
I'm working on that as fast as I can. I am trying to figure that out.
Okay.
So I didn't have as many people drop my 163 as I was expecting, which is good. That's a good problem. But I was expecting to have about half of them drop, which means I would have had time to put all the oral exams in that first week. But I still have 43 people in that class. So that's 20 some hours plus the grading time. I don't know when I'm going to squeeze in your oral exam. So I'm working on that. My goal is to figure out, you see, I had it here and then I took it down. I need to figure that out by Wednesday's class. So, and I'll send out an email as well as soon as I get that figured out. So my goal is to know what I'm doing about that by Wednesday. Is that cool on that question, Esteban?
Yeah.
All right. So regarding the quiz. There's a quiz next Monday on chapter 6. All right. So there it is. Now, if you haven't already been doing so, here's how, okay. And then, so what are we doing for, let me get my calendar here. Oh my gosh, it doesn't let me annotate. All right. Sorry. I'll just use the mouse. Sorry. So we're right here at the 16th. On the 18th, we are going to do just more practice problems, and you can skip class if you want. I probably won't live stream. I'll just be here answering questions. On the 23rd, you have the chapter 6 quiz. There is no new content for the rest of the semester. On the 25th, there's not going to be any class. I want you just practicing old tests. Okay. And so here's some old tests you could take. Now, if you want, here's all of my tests. Here's a study guide for chapter 1. Here's a study guide for chapter 3, etc. Chapter 2, 4, 5, and 6. One thing that we are not going to do, we will not do any circular motion problems. I'm going to save those. So notice there's a link to a practice final. There's going to be no circular motion. So I'll try, any circular motion problems, just skip them. And so you should be able to recognize those because there'll probably be a circle drawn in the picture. Let's take a look at this thing. Okay, here's some more practice problems, more practice problems. I haven't seen any circular motion yet.
2B was a circular.
Was it?
I believe.
I probably just went right past it. No.
Oh, I just saw the word circular.
Oh, that's this gasket. So that's one of those mass with a hole type problems. Sorry, I'll make it a little bigger. Yeah. See, I don't know if there are any in here, but let's check to be sure. Sorry, I'm taking so long. Yeah, I didn't see any in there, but maybe there was one that I missed. So if for some reason there's some different right? So there's a couple of extra problems here and I solved them for you. So if you want to know, basically, again, now this is, be careful. This practice final, I said, should take you 4 to 6 hours. So your real final is actually going to be about 2 hours. So you know, and I think it ended up being 11 questions, 11. And some have numbers and some don't. So some are algebra, some have graphs, some don't, some have I-hats and J-hats, all that crap. And then notice this note here, something that for some reason when I was writing that practice final, I totally forgot all the vector stuff, which is like the main point of this course, which I don't know why I forgot that. I was just in such a rush. But if you look back here, there's lots of practice tests that do have vector questions on them. So you can go through here and see. There's probably lots of good practice questions here. So if you want to get good at this class, there's all kinds of vector problems. Oh my gosh, more vector, vector, vector. So there you go. Just do all of these problems and you will get an A. If you do half of them, you might get a C. If you do less than half, you probably are not going to succeed. I'm not trying to lie to you. I just know from past experience. I've had students tell me they do one practice test and then they bomb the test. And they're like, I did a practice test. I'm like, well, take a look at some of the other ones. Not all questions can fit on one test. So if you only do one practice test, you just don't see enough. But after you've done, say, 2 or especially 3, you start to see the patterns. You could tell what's on every test. And then you can see the kinds of things that I pick and choose for the other ones. Finally, I'm going to point this out again. Let me go back into here. After you take these, grade yourself. Now, you probably are going to grade yourself nicer than I grade you. I am going to tear you up. This is your only paper submission. I'm going to look at it with a fine-tooth comb. So what does that mean? I'm going to expect you to write your answers correctly. For example, you should not be writing answers with 70 billion sig figs. That will make me crazy, and that will cost you points, right? Usually you do 3 sig figs unless otherwise specified, etc. And this goes through, you don't include units on an algebraic answer. So many times I see people write this and include the units. I just take off points. What about the I-hats and J-hats and units? There's the deals for vectors, magnitudes, directions, and unit vectors. For example, unit vectors have no units because they drop out, but they do have the I-hats and J-hats. Also, we see that vector magnitudes have no I-hats or J-hats, but they do have units. So, and the vector has both. So I'm trying to give you the time to do the practice test to succeed on the final. So that's why we're not doing any more class. It's just practice, 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 and I'll be available to answer questions. All right, I'm going to go ahead and stop the live.